So I think I'm recording. We are taking a look at the end behavior of rational functions. Rational functions are a ratio of polynomial functions. We want to know what's going on in the graph if you're very far away from the origin. So we compare the degree of the numerator against the degree of the denominator. The degree of the numerator here is written in standard form. The biggest exponent on my variable x is 2, so that numerator has the degree of 2. The denominator is not written in standard form, but it's written term by term, so I can just look at the variable x and find the largest exponent. That's 3, so I have a denominator that has a degree of 3. So I just refer to this as bottom heavy. Every time it's bottom heavy, it will have the end behavior is a horizontal asymptote. That as x gets very far away from the origin, either to the left or to the right, the graph is approaching the line y equals 0, which is the x-axis. And that always happens when it's bottom heavy. So I do not know the behavior of the graph yet around the origin, but I know that when you're far away from the origin, that you're going to be close to the x-axis. When you're close to the origin, who knows, you might cross it a few times, I don't know. And I also really don't know, when you're far to the right, is the graph getting closer from above and never touching it, or will it be coming at it from below, getting closer and closer and never touching it? That I don't know. The graph can tell me that, but they're not asking me for that. All they're asking me for is to recognize that when it's, as x approaches positive infinity, that the y values are approaching 0. And here, as x is approaching, so, I guess maybe I didn't write it out in the other videos or write it out in class, but, we could write this equation and say that as x is approaching negative infinity, the y values are getting closer and closer to 0. As x is approaching positive infinity, I claim that you'll find that the y values will be getting closer and closer to 0. So let's go see if that statement's a true statement. If I haven't made any silly mistakes, let's go check out the graph of problem number 4 on this Desmos graphing calculator. So let's turn off our previous work. Let's hit 4 here. Let's see. Let's zoom up, maybe to zoom in. Where am I at? Let's go to the left here and find the origin. Well, we can see right now we're real close to the x-axis, which is what we claim. Boy, I can't. Hey, I'm getting closer to 0. It's counting down. There we go. So, nope, zoom out. Maybe that's what I should have done to begin with. So it looks a little bit crazy close to the origin. You've got this wave. It's going up. It's going. But if we zoom out, when you're far away from the origin, see how it's becoming a flat line? We made the claim that we didn't know what was going on close to the origin. It could be acting kind of strange, a bizarre behavior. Oh, I erased my answer. I just have accidentally tilted that somehow. All right, so you can see I at one time had the x-axis highlighted here and here, so I've kind of somehow distorted my problem, so it's not really. You can look back in the video and you can see that, well, we can see right here that these claims right here are true. That as x is going to negative infinity, that you can see that the y values here are almost equal to 0. You're almost on the x-axis. And over here, the same thing. That as x is going to positive infinity, this graph is coming at it from below and getting closer and closer to that x-axis. So I'm pretty confident that we were correct in claiming that the horizontal asymptote was the line y equals 0, which, using our previous notation, you could do that. See, I avoided that because when we had this notation, y was always approaching either positive or negative infinity. We'll see here we're approaching some number. So we'll just keep with saying horizontal asymptote so that we don't confuse anybody more than what's more than what I already have. Sorry about that. I will talk to you later.